We are on number 3, so we're going to talk about one dimensions. We've been talking about 0, right? In the 0 dimension, we're talking about 1 dimension. So the first dimension is represented just by a straight line, which we can call the x-axis. It has infinite length. It can go on and on forever in either direction, but it doesn't have any height, doesn't go up and down, and it doesn't come out any. It has no width, it has no breadth, it has no length. All right, how do we define a point? A line is defined anywhere I have, can I make a line through this? I can make a whole lot of lines through this point, but there's an infinite number of lines I can draw through that one point, right? But if I want a line, I have to have, if I want a specific line, if I want to define a line, I have to have 2 points. Because if I can connect them, now can I turn this line anywhere else?
Nope.
No. That is this line. We can call it line H. Line H is defined by those 2 points. Any 2 points anywhere in space, you can draw them wherever you want, one here, one here. That defines that line. And what I mean by defines it, I can't change it. If I changed it at all, it would either go through one point or the other, but it could not go through both. So you need 2 points to define a line. And we talk a lot in classical conversations about definitions and how they're important, how they narrow down what a word means. So this is how we narrow down what the line is. All right, so we have the real number line. You guys have been using this probably for a very long time. So we represent the real number line with our real numbers. 1, 2, 3, all the way. You agree it can go up to infinity, right?
Yeah.
That arrow indicates it's going to go on and on forever. We can go the other direction too. We can have -1, -2, so on and so forth. Well, here's a question for you. Where on the number line is 1/2?
In between 1 and 0?
Yes, right there. Not there, right there. Right? So what about pi? Annalie, where's the number pi?
It goes in between 3 and 4.
Very good. It's going to be somewhere right here. 3.14159, right? So it's going to be right there between 3 and 4. Because this is a real number line, it represents all the numbers between 3 and 4, which would be 3 and 1/10, 3 and 1/2, 3 and 3/4, 3.141592653. Wherever that number ends, which we don't even know where it ends, it's on that line because it's a continuous line between those points. So between 3 and 4, there's actually an infinite number of points on any given place on the real number line. So we use negative signs to depict anything that is less than 0. We owe somebody money, it's negative money. We dig dirt out of a hole, we have negative space, right? We're digging. And we have positive numbers. We actually don't write a sign to indicate that a number is positive. Okay, so far so good. So now we're going to talk about some graphic representation. This, who can tell me what that is?
A point.
It is an A, it is a point, and it is an A. So what this is actually a point named A. All right? So when we draw a point and we draw a number, a letter next to it, we're naming that point. So that is point A. And we normally just say A, point A. Like we don't say, that's how we name, that's the name of that point. That's how we call it. All right, then we have what we call a line segment. A line segment has a beginning and it has an end. We name the beginning, it begins at a point, it ends at a different point. So when we name a line, we name it a line segment, we do AB. And we have a line above it, but there's no arrows on this line. So this is a line segment because there are no arrows. It's saying I begin at A and I end at B. I mean, for all I know, it could be C and A. This would be the line segment CA, which is the same as line segment AC, right? Because lines have no direction. Vectors have direction, lines do not. We're not there yet, but right? So they're the same. Then we have what we like to call array. Now, array has a starting point. So, hold on. When I go to a line segment, definite beginning, definite end. It's like home to CC. Home to CC. We are not going on and on and on forever. We have a starting point, we have an ending point, right? That's a segment. Now, the next step is if we have array, and if it were to go on and on and on and on, we're not stopping at CC, we're gonna keep going. We got a road trip and we're just gonna drive.
So like, like the array would basically be like if you're in space and you just like jump.
Yeah, and you just keep going, yes. On and on and on and on forever. We call that array, and how we write this one is we have to use the beginning point. And then the second one is any point on this line. It could be, we can call it a B, we could call this one a we could call it a C, as long as the first one is where we start, and the last one is any other point on that line, because it doesn't have an end point, right? So it could be any of them.
So like,
now, here's the trick. What if I did, and I'm gonna put my B over here, and I do this? How would I name that ray?
B.
BA. So this would be the ray BA because it started with B. So with a line, it doesn't matter, or line segment, it doesn't matter because it's the same. It doesn't have direction, but a ray does, right? So we're gonna start with our starting one and end with our other one. Okay. Then we have the next step is what happens if it goes in now both directions. This is what we call a
line.
A line, very good. You got your book open. A line goes infinitely in all the directions, both directions, positive and negative line, and you name it with, what did we say defined it? What did we say defined a line?
Just infinitely long with
It
no
is,
height.
but how do we define a line in space? How do we make it the exact line we want it?
2 points.
What were you gonna say there?
A segment.
Yeah, well, a line segment is a part of a line. It's like a chunk of a line. But to define a line in space, we need 2 points, right? Otherwise, if I have 1 point, we talked about how it could go anywhere if we wanted it to. To fix a line, which is defining it, we need 2 points. So to name a line, we have to name 2 points, because that's the definition of a line. That's why all of these bits and pieces of a line, like a line segment and array, is going to have 2 letters because we have to define a line using 2 points. So I can define this line as line AB, but put the arrows on either direction. That indicates it's an infinite line. It's not a line segment, it's not an array, it's a line. I could name it CF. I could name it BA.
Can you name it AJ?
I couldn't because I don't have a J on this line. If I had a J on this line, now I can name it AJ. All right. All right. So we're going to, then next we're going to talk about a vector. All right, now vectors have been showing up in math a little bit, and we haven't quite discussed what a vector is, but a vector has length and direction. So instead of just going on and on one direction or on and on another direction, it has a definite how far you traveled, and it has the direction in which you traveled. It's very important in science that you have both pieces. In math, we typically just talk about the fact that it has a set fixed length. So it's kind of like array, but the difference between array and a vector, if this is my ray, A, B, that actually goes on and on and on forever, right? And this is my line segment, A, B, which is the same as BA, right? So how do I specify I want to start at A and end at B? That is what we call a ray. And the only difference, a vector. it's going to end right there. A lot of times you'll see only half the arrow drawn, and it means that it's going to stop at B. And that just shows the direction. I started at A, I ended at B. So it's not a line segment. So with vectors, let's talk about this. If I were counting how many cookies are in the cookie jar, I would have 1, 2, 3, 4, 5 cookies, right? A vector is more, I went 5 steps. It's going to have a length to it. So it's actually a different thing than a counting number, right? Because a counting number, you're counting how many bits and pieces you have. You've got integers, right? And when you're counting length, it's a different thing. So vectors have a length to them, right? And then a break, if I have a line and I want this whole line except for between A and J, you just put a little break there.
Don't separate AJ.
Yeah, well, sorry. All right, so there's a couple of ways we can write,
Wait, so if you do that, is there a name for like what's in the middle? Like if there's still C in the middle?
no, it's just not part of the domain, which we're gonna talk about domain and range, I'm sure. I don't know, I haven't looked at all the math yet, but I'm pretty sure that that's gonna come up a little later. It's what things you can input versus output, and these are just unusable terms, okay? For right now, we're gonna call it a break. If I wanna measure my line segment, which has definite length, I would put a little m. So I put m, measure of AB. Can I have the measure of line AB? No, that would make no sense because line AB goes on and on and on and on and on and on forever. Can it have a definite length?
No.
No. So that would make no sense to talk about line AB that way. Would it make sense to make measure of AB the ray?
No.
No, because it would be infinite because rays go on and on and on and on and on and on forever. All right. Do you think it would make sense? Here's going to be a trick question. To find the measure of vector, which I didn't tell you how we do this. For vectors, we typically give it a little like letter. Vector U. Yes. However, how we normally write it is this. It looks like an absolute value sign. It's the magnitude of vector B, or the length of of U. So that will tell me the length. Well, we know absolute value is how close it is to 0, right? With the number line, we kind of get rid of the negative sign. It tells us how close it is to 0. So with vectors, that's how we write it. Fun stuff. All right. What time? How am I doing?
20 minutes.
Oh, good. We're doing great. We're doing great. So let's talk about different kinds of axes. We talked about our real axis. There's a couple of other axes that you will deal with in math as you get further and further along. Instead of just talking about real numbers, this class we've been learning about imaginary numbers, right? Who can remind me what I is in the imaginary numbers? What does I stand for? Yes.
Square root.
Square root of, remember? -1.
I do that.
Yes. So it's a specific one. Now this was on our math map for last week. I didn't get to talk about it a lot, but remember, so if I is the square root of -1, because square root is saying what squared gives me this number, right? I'm rewinding to last week just a little bit because this whole year is on complex numbers, so this concept is super important. So if I had the square root of 25, I'm asking what number times itself gives me 25. That's easy.
5.
5. Wait a second. Could it also be -5?
Yes.
-5 times -5 does in fact equal 25. Well, this is what we call the principal root. So if we don't actually write the 25, if we don't actually make the square root symbol, if it's part of the problem, we only care about the positive number. This is when we're solving algebra, we need both the plus and the minus. So keep that in mind. All right. Question. Can I do any number times itself and get negative 25?
No.
No, because I can either do positive and negative 5, but wait, that's not the same number. Is it? No. And if I made them both negative, wait, I'm back to positive 25. And if I switch it, there is no way to multiply any number times itself and get a negative. Oh no, we cannot physically do that. But it does come up from time to time with the numbers. So that is why I was created, right? So what we can do is if I have the square root of negative 25, I can be like, I cannot physically make a number times itself be a negative number. So we are going to pull out that square root of negative 1 and then multiply it by the square root of 25. And we're just gonna simplify things and call that the letter I. That turns into the number 5. So we normally write the coefficient first and then the I. 5I. Okay? You will never have a power of I. Okay? We didn't get to talk about this last week, but this was last week in your math, so some of this should look familiar. Why won't we ever get a power of I? I'm afraid if I go over there, it'll block half the classroom, so I'm gonna just erase it. So, let's say, why does I never have a power? Let's explore. I squared.
Negative 1 is the square root of negative 1 squared, and the square root and the square cancel. This is negative 1. I looked at that, I'm like, that is wrong. It is negative 1. Because the square root undoes the square. It's saying what times itself is giving me that. That's negative 1. All right, why don't I have an I cubed? Well, I cubed is I squared times I. Right? I squared is negative 1. So I cubed is just negative I. And then I have I to the 4th, which is I squared times I squared. Which is negative 1 times negative 1, which is 1. And I can keep going on and on. I to the 5th, right? It's I to the 4th times an I. Well, I know that I to the 4th is 1. So it's just 1 times I, which is just I. So I to the 5th goes back to I.
So does it?
I to the 6th is going to go back to I squared, which is still going to be negative 1. It kind of keeps repeating. It's a pattern. It would go on and on forever. So we never have a power of I, because it will either be I. If you see an I squared, you simplify it to negative 1. If you see an I to the 3rd power, you simplify it to negative I to the 4th power, it goes to 1. And so on and so forth forever and ever. That was last week's math. Yes.
How do you negative something that's already negative? Since I stands for the square root of negative something, then how can you make that negative? Wouldn't the negatives cancel out?
Because of the properties of square roots, you can't just pull a negative sign out of a square root. That's kind of like saying 4 times the square root of 4. Can I multiply this 4 and that 4?
No.
No, because on the way out of the square root, that's going to become something else. It's going to be 2. That function, that square root function, has to be applied to that 4 first before we multiply it. So if I have a negative times a square root of a negative 1, that negative can't just come out of that function, funsies. It's got to have that function applied before it can come out. So yes, you can have a negative I. Very insightful question. Good job. Okay, so that was that. So all this being said, we can have an axis. We talked about our real axis called our imaginary. Our imaginary axis. Then what we do is we call this I. And I'm sure we will be using this imaginary axis this year in complex numbers. It looks just like our real axis, which has all of our real number integers, except for this is going to have all possible complex numbers. Imaginary numbers, not complex, but imaginary. Remember, we can never have I to a power, right? So we're going to start with 0 right in the middle. And I can go up by 1 I, 2 I, 3 I's. And if I go down, I can have -1 I, -2 I, and so on all the way to infinity, right? So we can have an axis, which is just a line, that's going to tell us our imaginary numbers. Now when we get in 2 dimensions, our real numbers and our imaginary axis are going to intersect. All right, and that's when we get complex numbers, because we learned already this year that complex numbers are a real number plus an imaginary number, right? A plus BI. All right. Do you have a bigger eraser? Midpoint. You guys all already know how to do midpoint. It's the average. Do you all know how to average things? Yes, okay. So if I have the midpoint between the numbers 2 and 4, what is the middle number?
3.
3. Everybody can do that. Well, you did that without doing any math, but what's the math you did? You took and added them up, and then what did you do? Divided by 2. So that would have given me 6 divided by 2, which is 3, which is in fact what we got, right? So what we're doing is we're kind of connecting 2 to the end of 4, and we're cutting that length in half, and that would tell us exactly the middle of the whole segment. So that is what we call midpoint. And your book gives you a formula. If I have an A and I have a B, and the midpoint is M, what is my midpoint? It's going to be, they actually do x1 plus x2 over 2. Don't let that confuse you. 0.1, 0.2 over 2. They're using x's because this is a horizontal axis, which we typically call our x-axis. Because you can find midpoints in space when we add a second axis or a y value. But right now, we're only working in 1 dimension. So the reason they used an x is because these are just, A and B are just standing in for an x. You have one and then you have a different x. So those little subscripts tell you you're talking about 2 different points. All right? So that is midpoint. We can also do distance. We can also do the distance between point A and B. So what is the distance between 4 and 2?
2.
2. The distance. How did you do that? How did you do that? You counted. You literally went 1, 2, right? You could have also done 4 minus 2, right? You could have also done, 2 minus 4, but that would have given me -2. That is when we include these absolute values, because distance, negative doesn't matter. Whether I'm going from here to CC or from home to CC or CC to home, I'm going to have a distance of 2. So that negative doesn't matter. So what we use is we use these absolute value signs. And that tells me how far from 0 am I. So if I were to look at a number line, and I were to look at 3, what is the absolute value of 3? What I'm asking is how far is 3 from 0? It's 3 units. But it also matches, if I were to take the absolute value of -3, how far from 0 is -3? 3. It's still 3 units, right? So effectively, the absolute value is erasing the negative. But what it means is how far away is it from 0. So when we do a length of a segment, you subtract the 2, but you put them in absolute values because negative doesn't make any sense when we're talking about the distance. Okay? All right. I got 1 page done. Let's go on. I'm going to skip that bottom Inequalities, you guys showed me last week already that you know greater than, less than, greater than or equal to, less than or equal to signs. So I'm not gonna spend most of our time, you guys all were happy with the alligator or the Pac-Man eating the bigger number. Okay, great. Scientific notation. So, okay, there's a typo in your book. I'll try to work through that. But scientific notation, it matters when we measure. It matters when we measure with instruments what the measurement is going to give us. So if I were to go to a football game and I were to say, hey, there's 500 people here. Do I actually think there's 500 people there? Do I know? Or am I guessing? It's a pretty good guess. But if I was collecting tickets, and people were paying me and I said, there's 500 people here. What do I mean? There's exactly 500 people. So 2 scenarios. What if 2 more people come in? If 2 more people show up, does my 500, when I guessed it, does my 500 change or is there still 500 people? There's still 500 people. Like 2 people coming in the door isn't gonna change my number. But for the person who's collecting their money, 2 more people came in. Did that change their number?
Yeah.
They now have 502 people. And that is what we call precision, not accuracy. That's wrong. It says accuracy. Accuracy is how close you are to the actual number. Precision is the instrument being used. It's at the bottom where it says significant digits. Okay, so significant digits means sometimes numbers have a meaning and are importance, and some numbers do not. So if I were to say my 500, this 0 had no meaning because I was guessing. The only number that had meaning was this 5. So we call that a significant figure or a significant digit. All right, whereas the lady who was taking counting, she has 1, 2, 3 digits that are significant because she actually cared about those 2. So she knew for sure there was 500. There were none of the 10s, and there were actually 2 people. So she had 3 significant digits. I only had 1. So who was more precise? Her counting, not my counting. All right? So it is important when we add numbers, if I'm adding something that is significant to something that is not significant,
What about, like,
that I pay attention to the digits.
what about, like, since, like, you both got, like, the first 2 right, why isn't the 0 right on yours?
That was just luck. That's all depending on the instrument. I was not counting to the 10s. Now, maybe I did. Maybe if I was counting, like, if the seats were in rows, and I was like, it's about 500, you know, and I was only off by 10, but I doubt it. I'm not that good of a counter. So, running out of time. Okay. Let's talk about significant digits. Any 0 is not significant. Okay, I'd like to start at the decimal place. If I have a decimal that looks like this, any of these that are before the number are not significant. That'd be like me writing 0005. There's still only 5 candies. None of those matter if they're left of my number. They don't count. They're not significant. They have nothing to do with the instrument I use. It's just they're placeholders. Anything to the left of the number is a placeholder. So this would only have 1 sig. I'm gonna call it sig because that's what I'm used to. All right, 1 significant figure. However, if it's at the end, if I had 0.000050, that is significant. Only because it's to the right of the decimal, because that means I actually measured to that place. If it's not a decimal, and let me go back to my 500, these are placeholders. Because they're before the decimal, those count as placeholders. Whereas in a decimal, those guys are placeholders. They're just filling in gaps until I measure, right? So I measured the hundreds, I did not measure the 10s or 1s. So this only has 1 sig. So for decimals and whole numbers, the rules are just ever so slightly different. But the zeros in between numbers are significant. So let's go back here to 502. There's 3 significant figures because I now know my ones place is significant, and you can't count your ones without counting your tens, right? So that is why the zeros in between are significant. So you want to know how I'm going to make this more than one sig fig? Watch this. If I add a 1 right here. Now all these zeros, which were just placeholders, now since I had to measure a 1, and I measured the 5, it actually means I measured 0 on all these other hash marks. So I got 1.0005, so that would actually be 6 significant figures, because now they're not just placeholders because I measured that guy. Okay?
So it's like everything past a number that's not 0.
Yes. Well, it depends on if you're looking at a decimal or a non-decimal. And then, it's time?
Yeah.
Okay, I was gonna do sig. The reason we do scientific notation is because you have sig figs times 10. But I didn't do that because I think most moms can